If we can show that molecules also have natural frequencies of vibration and can understand how light waves interact with them, then we can see why a molecule will absorb infrared radiation only at certain frequencies. If the frequency of the light wave is the same as the natural frequency of vibration of the molecule, then there'll be synchronization. The molecule will absorb energy from the light wave, and the molecule will vibrate more and more vigorously. Now, the way in which the light wave lays hands on the molecule has to do with the fact that the light wave is accompanied by an oscillating electrical field, while the molecule has different electrical charges on its different atoms. The left to right electrical field will push the positive atoms a little to the right, negative atoms a little to the left, and the right to left electrical field will do just the reverse. We can reproduce this condition by using an electrical generator to charge two condenser plates. With one charged positively and the other negatively, we can switch the charges back and forth and simulate the oscillating electrical effect of a light wave. To model the hydrogen chloride molecule, we can use two lightweight spheres connected by a spring. These, of course, represent one hydrogen atom and one chlorine atom, held together by a bond. The spring rather accurately represents the bond. We have put a positive charge on the hydrogen and a negative charge on the chlorine. With this motor, we can switch the charge on the condenser plates back and forth, and we can observe the effect of the oscillating electrical field on our model of a molecule. We start with the system at rest and slowly increase the frequency of the oscillating electrical field so that in effect we scan the spectrum of different frequencies. At first, there is no interaction between the field and the two charged spheres, but when we reach a certain frequency, which corresponds with the characteristic frequency of our mechanical model, we see that the model begins to vibrate. Its vibrational energy is derived from the oscillating electrical field. We'll slow this down a moment to compare it with a molecule interacting with the oscillating electrical field of a light wave. They will interact strongly when the frequency of the light wave is the same as the natural frequency of the molecule. But if we increase the frequency still more so that we exceed the characteristic frequency of the system, we find that again there is no interaction. The energy of the wave is not absorbed. Because of frictional losses, the model quickly comes to rest. In the case of a real molecule, its energy wouldn't change. Now we've seen how a diatomic molecule produces its typical infrared vibrational spectrum. Let's go on and consider what happens in the case of polyatomic molecules. We can learn something about their vibrations by the use of a model of the carbon dioxide molecule. The center sphere represents the carbon atom, and the oxygen atoms are on each side. These are all connected in a line by bonds, which we've again represented by springs. Let's see how this model of a carbon dioxide molecule vibrates in its own particular way, just what sort of natural frequencies it has. We activate the model by using a motor-driven eccentric, which is coupled to the molecule by a very loose spring. Of course, if this were a real molecule, it would be pushed on by the oscillating electrical field of the light wave, just as we saw in the case of the HCl molecule. As we attempt to excite vibration very slowly at first, you can see how the molecule flops around rather loosely, but doesn't really fall into any organized, repeating pattern of vibration. When we slowly increase the frequency, we reach a point where the vibration of the molecule falls into a nice characteristic pattern called a normal mode. The molecule has reached one of its natural frequencies of vibration. At this particular frequency, it can vibrate in the normal mode you see here, with the molecule moving its atoms perpendicular to the bonds or springs, with the carbon atom moving up at the same time the oxygen atoms move down. Now, as we turn up the frequency, we once more leave the regular pattern of a normal mode, and the molecule falls into wild, chaotic motion with no regular pattern to it. As we increase speed, we reach another normal frequency where the atoms begin again to execute a smooth, characteristic vibrational pattern. We note that at this frequency, the molecule has its atoms moving along the line of the bonds in a nice symmetrical fashion, with the two oxygen atoms breathing in and out and the carbon atom staying fairly still. By increasing the frequency again, we get away from synchronization, and the molecule again shows only chaotic motion. As we approach the third normal frequency, we see that the molecule is moving in an unsymmetrical fashion, with the carbon moving one way and the two oxygens the other. We would find the same three characteristic types of motion in the actual carbon dioxide molecule. It would move like this at a frequency of 7.05 times 10 to the 13th cycles per second, the highest natural frequency of vibration. Like this at 4.16 times 10 to the 13th cycles per second. And like this at 2.00 times 10 to the 13th cycles per second, the lowest natural frequency. These three frequencies are all the components we would find in any vibrations of carbon dioxide, and any motions can be analyzed in terms of these three characteristic patterns. Now we've seen that CO2 has this motion, and this motion, and this motion. Any polyatomic molecule has a finite number of such characteristic patterns, each with its own definite characteristic frequency.